Talking about taking some vehicle routing problems and turning them into video games. And this is some work that I've done along with an intern, Kullman from the University of Tours in France, along with Jorge here and Martin Cousineau from HEC in Montreal, and Justin Goodson at St. Louis University. So before we jump into the presentation, I want to give you a quick preview. So we've had some success here. It did not come immediately, as we will see, but we have trained an agent to play some version of a vehicle routing problem. Okay, so since we've had access to high-performance computing, we've been trying to train computers to beat us in games that we have invented. It's kind of interesting. And I think the first prominent example of this was IBM's Deep Blue, which beat Garry Kasparov at chess in the 90s. And since then, we've seen sort of an explosion of success in this area. And a lot of it has been driven by deep learning, this method that has been around for a while, but has only recently become viable due to the availability of more and more data and cheaper computing power. So recent successes include chess. So we've now, we have some deep learning trained chess players that are better than Deep Blue and the existing human professionals. The ancient game of shogi and Go. And then recently, this was kind of exciting, StarCraft. Very impressive work. And pretty much most of these are coming out of one team, DeepMind from Google. But the example that we're going to talk about today is Atari. So Atari was an interesting case because it was sort of viewed as a step towards general artificial intelligence. So there was a single agent that was trained to play a handful of Atari games successfully. So across a suite of different Atari games, there was one agent that was able to beat existing benchmarks and in some cases professional humans at these games. And these games are fairly diverse, right? So I say that they have different selves, which means that you're not always controlling the same object. So in Pong, for example, you're controlling a paddle that moves up and down. And in Breakout, you're controlling a paddle that moves left and right. In Space Invaders, you're this little guy at the bottom of the screen that's trying to shoot the aliens. And in Sequest, you're a submarine. And so these things look different visually, but then also the actions that they can take are different, right? So in Sequest, the submarine can go up, down, left, right, and it can choose to shoot things. In Pong, you just go up and down. And these things have different objectives too, right? So, I mean, ultimately they have the same objective, which is to maximize your score at the end of the game, but your objective here is, as a player, is to move this ball past your opponent. And here your objective, in a lot of these, your objective is to just not get blown up, or to kill the most enemies that you can. So the point here is that these are a set of games with diverse action spaces and set of controls, and yet this one agent could tackle all of them. And so the idea is, okay, is there something special about this original set of Atari games that makes it possible for this agent to win in this environment, or could we make a game of our own and then train an agent in the same way that that they did with the existing set to play our own game? And as a couple of vehicle routing people, we said, okay, well, let's see if we can make a vehicle routing game and see if this agent can play against us and beat us at this game. So that's the idea. So in this new paradigm, this idea where we're going to use Atari. So in this case now, Atari is the console, which is basically our model. So instead of using like a math program or markup decision process, our problem model is this visual representation, sort of this Atari. The games for Atari are the different problems or the problem variants that we might consider. Right, so we might have a simple game like Pong, which would, something like the vehicle routing problem. We might have another game for the vehicle routing problem with stochastic demands or stochastic travel times. And then we have this agent, which is sort of a general purpose solution method, which I guess more specifically would be deep reinforcement learning, that learns to play these games, to solve the problems that we build for our new console, these new models that we drive. So the benefits of this. So the first one that I've kind of touched on here is that it's flexible, right? So any vehicle routing problem that you can visualize it's possible that you could model it as an Atari game. Again, if you can have some set of customers across the screen, it's not too difficult to imagine that you could introduce time windows by maybe changing the color of these things based on how much time is left, or something like that. At the same time, video games are inherently stochastic and dynamic environments, right? So if you knew exactly what was going to happen in a video game, it wouldn't be a very interesting video game. There's lots of revealings of uncertainty. And so the problems that could be most effectively modeled as video games are ones that involve a lot of stochasticity and dynamic decision making. And these are problems that have been traditionally more difficult to solve with things like math programs. And so if this solution method works, if posing things as video games is successful, then maybe we have a whole new avenue that we can use to pursue solutions to these stochastic dynamic vehicle routing problems. Okay, so that's the idea. So now let's take a quick look at the agent that was developed by DeepMind to solve this problem. Okay, so what does the agent observe? So the agent gets a stack of consecutive frames from the game. These things are downsampled, and then we grayscale them. And so basically the input is something like this, where you have a frame, your ball is here, and then your ball is moving closer and closer. Okay, but what does it really see? So when we look at an image like this, we have a biological neural network that helps us interpret what it is that we're seeing, right? So we see a picture here that makes some sense to us. But what the agent actually sees is just basically some stack of arrays that have some numerical value that indicate the color of a particular pixel. And given this information, what does our agent want to do? And so obviously it wants to maximize its score at the end of the game. So it wants to choose the best possible action, which is the one that maximizes the immediate reward plus the reward to go, right? So how do I get the most points? By making an action now at the end of the game. So what this looks like, so I should mention, so this, as we've seen in a couple other talks already, this value for choosing a particular action from a particular state is known as a Q value. So this is deep Q learning. And the Q values from these different states, for example, so we see here the agent is pretty optimistic. So 1 here means that it thinks it's going to win the game. -1 means it thinks it's going to lose the game. We see here as the ball's approaching, it's optimistic, thinks it's going to win. And it thinks that no matter what it does right now, it's going to win. As the ball gets closer, it says, you know what, things do not look good if I do nothing or I move down. But I think if I move up, I will probably win this game. And so then the ball gets closer and the signal gets a little bit stronger. And then in this state, we've now made contact with the ball and we've sent it flying back across the screen. And the ball is just about to cross our enemy's threshold, which means we are about to earn a point, which means that the expected cost to go, no matter what I do right now, I'm going to get that point in the next step. Okay, so how does our agent learn these Q values? So it uses deep reinforcement learning. And the way that it actually accumulates knowledge of the value for these state action pairs is just play the games many times, basically choosing actions randomly. We remember the moves that we play and the scores that we got, and then we occasionally draw on those memories to update the weights of our neural network, as we've seen in a couple other talks this morning. Okay, so just want to emphasize this as we go forward. There's different ways to look at this input. Again, the neural network, humans would see something like this as the input to the neural network, but what this really looks like is just some value in 0 to 255 for each pixel in the input here. Okay, so now let's talk about the game that we developed to try to let this thing loose on. So we chose the vehicle routing problem with stochastic service requests because our members of our team have some familiarity with the problem. So what does this problem look like? So we have a single vehicle that starts off at a central depot, and we have a set of known customer locations, places where customers might request service. And we know some of these customers are already requesting service, but we don't know when or if the remaining customers will request service. and our agent wants to serve as many customers as possible before the end of some time horizon t. And this time horizon is captured with this, this time bar up at the top. You can see it shrinking here. So this is the visual representation of our game that we're using. And our agent wants to achieve this objective through choosing actions, which are just move up, down, left, right. And when we cover an active request, we're going to earn some reward for that. Okay, let's look at the numerical results. All right, so let's talk about what we'd like to see. So in the existing work from DeepMind, when they let their agent loose on these problems, they see something like this. So as you perform more and more training, your score on a particular game gets better and better. So this is for Space Invaders here. Agent originally knows nothing and it doesn't do very well, and then it learns Q values and it starts performing action selection much better. So this is what we're going for. So let's see how we do. So okay, so we started off with the original setup. So we pass it 4 consecutive frames, and we're going to downsample them and grayscale them just like in the original study. So input looks something like this, but then grayscaled. That didn't work out so well. Okay, so we're going to keep track of how we're doing over here. So 1 loss. We say, okay, you know what? Our problem actually isn't all that visually complex. There's not as much changing as in some of these original games. So maybe we don't need that stack of 4 consecutive frames. We can just pass it the most recent frame. So okay, we'll just pass it this most recent frame, again, grayscaled. That did not work either. I say, okay, well maybe we stripped away too much visual information. So now we're going to add in a couple additional layers. So instead of grayscale, we're going to do a layer for red, green, and blue. So this provides some additional visual information. And that did not work. And so we said, okay, you know what? So these games rely on, basically your agent has to be able to interpret what happens when it chooses a particular action, right? So the only thing that's changing here is the value of some of these pixels. And so when it moves this agent around, the change in pixel values really isn't that large, right? So if I choose to go up 1, most of these pixels look the same from epoch to epoch. And so we also had this time bar up here that was shrinking with each step. And we thought, okay, you know what, maybe this the shrinking of the time bar is sort of confusing the agent. It's providing some noise in this visual signal. So let's strip that out. We're just going to pass the game board, basically. And then on the side, just passed into our neural network, we're going to provide time just as a scalar, as a float value. That didn't work either. Okay, well, you know what? Maybe there's something wrong with our network setup. So let's try stripping it down. Again, our game perhaps less visually complex. That didn't work. Okay, we're still really excited about this idea. And there's some consolation in this because, I think machine learning engineers in practice would say that you spend the majority of your time massaging your input to this network and maybe your output as well. So the fact that we're struggling here, this is commonplace, and it's worth the effort to keep plugging in. Okay, so simplifying our neural network didn't work. Let's try beefing up our neural network. That didn't work. Okay, maybe there's something wrong with our optimizer. No, that's not it. Maybe we need to do some hyperparameter tuning. No. Okay, what if we tell the agent which actions are and are not feasible at a given epoch? No. What if we change the rewards that we're giving to our agent? Maybe it gets 100 points instead of 10 or something. That didn't work. Okay, what if we clip the rewards? What if, there's some maximum and minimum amount of reward that you can get? That didn't work. Okay, well, what if we implement some of these tricks that are known as the reinforcement learning rainbow, where you do sort of n-step learning, you use a double Q network, and then you use some dueling architecture, whatever. That didn't work. So we tried a lot of things, and we lost a lot of times. We racked up pretty impressive score there in the loss column. So what we saw, in summary, is that we're not very good at designing video games. So I think this is the point here. So right, it all depends on the visual representation of the game that you give this agent. And so my feeling here is just that the folks that designed Atari are much better at creating visual scenes that represent to the player what it is that you're trying to do and how you win. And so maybe our just grayscale board with the box that's moving around, some other lights in certain regions just isn't cutting it. It's not visually interesting enough. So anyways, in the end, we found something that did work, and this just happened recently, and I was really worried for a long time that I was going to show up this morning and just tell you about all of our failures and have nothing positive to show you, which isn't the message I want you to remember from this morning. But what did work was a somewhat less sort of naturally visual representation of the state. So what we're going to do is we're going to use a particular picture or a channel for each type of object in the problem. So what I mean by that, so we take our sort of original game board and we're going to strip it down into components. So we're going to pass in one layer for the vehicle. So here's a dot representing where our vehicle is. Here's a layer where we have dots representing where our active customers are, and another one for where our potential customers are. And then again, we're going to pass the percent of the amount of time remaining as a float on the side. And so when we use this representation of the state, we had some success finally. And if there's a premature round of applause, that's okay. So we did see finally some improvement in our scores over time. And here's that visualization of that agent going up here and collecting rewards. Look at it go. This is very exciting. And I think I cut the GIF right around here because it never actually goes down to the other clusters. I thought I cut the GIF. I should have cut the GIF. So in conclusion, so this is still a work in progress. So in conclusion, with some effort, we were able to use deep reinforcement learning to successfully tackle a visual representation of a classical vehicle routing problem. And I emphasize with some effort. So despite all of the failures that I showed you this morning, I think this is a worthwhile approach to keep in mind. So performance always varies by game. So in these, even in the paper published in Nature by DeepMind, there are still games that humans and previous benchmarks will outperform their agent on. So perhaps we just chose a very challenging game as our first attempt here. And it's also flexible, right? So I mentioned that any vehicle routing problem or any sort of problem that you can visualize and think about a way to stick it on some sort of pixel map, there's the potential that this modeling paradigm would work for you. And I also think that a lot of these model formulations, the games that we develop, if this catches on, are shareable. So this existing thing here, I mentioned an idea that I would like to pursue if I had infinite time is let these things change colors over time and then eventually disappear. As time goes on, if these things have time windows, a customer has to be served by a certain time. As this color gets darker and darker, it fades away, and eventually it's no longer possible for our agent to earn points on that thing. And I think it's pretty obvious that don't throw out your math programs and heuristics yet, because they're still substantially better than the performance that we've seen so far. But again, it hasn't been a complete loss, and I think this is exciting, and it has the potential to at least see if there's some problems out there that this would work on. And with that, I'll take questions.